Hey, welcome back to part 3. Just kind of thinking to myself, I never really finished this one up here, so we probably should take a moment and go ahead and do that. So if I look at the dot product, what this says to take my partial with respect to x, which we already know is, so if I look at the dot product, my partial with respect to x, which is going to be e to the x y times negative 1/2 plus the partial with respect to y, which we know as, e to the xy times x plus 1, right there, and multiply that by root 3 over 2. And that would be our directional derivative at any given point along with having that direction. And if you notice, it is pretty much the same as what we did up here above. Again, this is more of a generic case. All right, so let's take a look at an actual example, a real-world application. So you're watching a fly move, okay? You're watching a fly move through space. By the way, that's kind of how Descartes came up with the Cartesian plane. He was watching a fly, and it landed on the ceiling one day when he was sick, and he thought it'd be a great way to find out where that fly is at. So that's how he came up with the Cartesian plane. He just came up with some coordinates. And where the fly landed, he can find out where it went, and using, of course, Pythagorean theorem, he can find the direction and distance that the fly moved. Anyways, that was Descartes. Alright, he thought, therefore he was. So given a fly moves through space is defined by the following surface equation. If its location is at the point 1, 1, 0, so this is where it's starting, and it wants to move to the point 1, 0, negative 4, so that's where it wants to end. We want to find the steepness of the flight. So we're looking for duff, basically. Now, I can get my partials, but the one thing we don't have yet is the direction. So let's start with our partials first. The partial with respect to x is just going to be, let's see here, the partial with respect to x would be y squared minus 4, and the partial with respect to y would be 2xy plus 3. Now, we're moving towards this direction, so we have to come up with an initial starting point, and that's right up here. But notice, it's 1, 1, 0. My initial starting point, though, would be 1, 1. So I am going to find the change in the x direction at 1, 1. Because remember, we're just looking at the x and y coordinates. Remember, our derivatives in terms of x and y. So at x, 1, 1. And if we plug that in, we just get negative 3. Same thing with the y, the partial with respect to y at the point 1, 1. And we get 2 plus 3, which is, of course, 5. Now, the only other thing we need, though, is the direction vector. That's u. We need u, which is our direction vector. Now, it is going to be normalized, so we want to make it as a unit vector. We'll deal with that when we can. So let's go and get our direction vector. To do this, we're going to take our endpoint minus our start point. So in other words, we can take that point 1, 0, negative 4, minus 1, 1, 0. And if we do this, we're going to get the point we're going to get. Now again, I'm not really interested in the z coordinate, so I don't really need these two right here. I'm really only interested in the x, y part of it. And if we do this, 1 minus 1 is 0. So we get 0. 1 minus 0 minus 1 is negative 1. And yes, this is a unit vector. So now I can get my direction, my steepness of it, or product. So where I am going to use the dot product form, remember it's this, fx, fy, dotted with, well, remember this is my cosine of theta, sine of theta, so that's going to be our direction of our direction vector. My cosine of theta would be 0. My sine of theta would be negative 1. Man, we even know where this is going, right? If I'm heading, my direction vector is heading down, 0, down 1. So we even know which way we're heading, right here, negative 1. And if we simplify this, this is really saying negative 3, 5, right? Fx, Fy, dotted with 0, negative 1, and we would get 0 minus 5, which is negative 5. Now remember, this is the steepness, or the change in the z coordinate in the direction of u. That's direction of u. So, very easy to do. So let's take a look at another one. Alright, the same phi, it now arrived at the point 1, 0, negative 4, and it wants to move back to the origin. Now we know the origin has the coordinate 0, 0, 0. Again, we want to find the steepness of the flight at that instant. So again, we're looking for Duffman. So let's go and find our partials. Now our partials are basically the same, but now my starting point is going to be f of 1, 0. So I want to find the partial of x, and with 1, 0, plug the 1 and 0 in. I'm just going to get negative 4 here. My partial with respect to y, come up here at 1, 0, is just going to be, of course, 3. My direction vector, to get my direction vector u, I am going to take my endpoint. Remember, I'm only interested in the first two coordinates, x's and y's. 0, 0 minus 1, 0, and we just get negative 1, 0. And again, this is a unit vector. So now I can find my directional derivative. Again, I'm going to use the dot product, fx, fy, dot that with my directional vector, negative 1, 0. And if we do this, we would get, this is what, negative 4, 3, dot that with negative 1, 0. We would just get 4. So there's the steepness at that point. Are we heading up? Or are we heading down? Are we increasing or are we decreasing? So we can use these a lot of little word problems as well. All right, last example for the day. All right, the fly, after arriving at the origin, wants to move up. Remember the origin, that's 0, 0, 0. Wants to move up at the greatest possible rate. Oh, we've seen this before. This is a maximum. What direction should the fly go, and what will its steepness be? All right, so what direction do we want to go? Well, this is a maximum value. Therefore, we've done this before, we want the rate to be the maximum, the greatest possible rate. So, of course, we're going to look at the directional derivative, but we want to find out where the directional derivative itself is the greatest. So we have to take its derivative and set that equal to 0. So we want to take Duffman prime and set that equal to 0. So let's go ahead and start this. Ready? Our partial with respect to x is just y squared minus 4. The partial with respect to y was 2xy plus 3. Now we don't know the direction this time, so we're going to keep it generic. So when I look for my directional derivative, it's going to be y squared minus 4 cosine theta. Remember, that's my rule up here. I'm going way up here. Y cos times cosine theta plus the partial with respect to y times the sine of theta. And then go way down here. So that becomes plus 2xy plus 3 times the sine of theta. Now, we do know the point. So at the point 0, 0. So if I plug those in, our directional derivative then becomes negative 4 cosine theta plus 3 sine of theta. Now, for reasons that are going to be important for us very later on, direction and where we're heading is important. Notice, where are we going? Well, we are going left 4, up 3. So we are going to go, if I look at a coordinate system, whoops, hold on here. We are going to go left 4, up 3. This puts us in quadrant 2. We're going to be in quadrant 2 for our final answer. That becomes very important, especially when we start looking at direction. All right, so let's go ahead and continue this. So we want to find the maximum possible, so we are going to take the derivative now, f prime, and that becomes 4 sine theta minus 3 cosine theta, and if we set that equal to 0, we would get, and if I solve this, this is going to be kind of crazy, okay? We get 4 sine theta equals 3 cosine theta. So in other words, we would get the tangent of theta, whoops, that should be a plus, and that makes that a minus. We would get the tangent of theta equals negative 3 over 4. So there's almost our direction. So get the direction, solve for theta. We would get the inverse tangent of negative 3 over 4. But you have to remember, in arc trig, this is in quadrant 4. Remember, in arc trigs, tangent is positive in the first quadrant, but negative in the fourth quadrant. So this is in quadrant 4. We want to be in quadrant 2, so how do you go from quadrant 4 to quadrant 2? You add pi, or you can subtract pi. So we would add pi. And by adding pi, now we are in quadrant 2. And there is our answer right there. Remember, this is in quadrant 4, but we want to be in quadrant 2. And of course, then if you want to find out the steepness, you just plug theta in for this, and you get your answer, of course. All right, I hope you enjoyed the videos. I enjoyed teaching it. I'll see you guys later. Bye-bye.